Alrighty then, we're going to talk about triangles. We do not say that other T word that is so darn scary that you might think that you can't do it. Because if you think you can't do it, you might not be able to do it. But if you don't realize what you're doing until you're doing it, you could probably get there no problem. So we're not going to use any phrase to describe this activity except triangles. Because triangles are simple. You guys remember triangles from being a kid? They're easy. Whoop, kick everything around. All right. Now, you'll be wondering why there was such a gap there. Okay, so we have just a basic right. All the triangles we study are right triangles. The book talks about Pythagorean Theorem first and foremost, right? And we don't use that. We do not use Pythagorean Theorem. Okay, the Pythagorean Theorem, we even write it a different way. Everybody, all the math teachers of the whole world write c squared is equal to a squared plus b squared. We don't do that. H squared, the hypotenuse squared, is equal to a squared, the adjacent squared, plus the O squared, opposite side squared. But even at that, in electrical, unless you don't need to do anything else, we don't do it that way. We do it with these functions. And these functions have names. And they're very simple ideas, okay? They really are. The sine of anything is the opposite over the hypotenuse. That is this side over here. Here, let's name these sides before we start. This angle right here is always, and we're going to draw this exactly like this. I don't care how it shows it anywhere else. We don't care about how other people do it. This is how we do it. We are electricians, and we do it this way. We always draw the angle to the left, the right angle to the right, and we either go up for this side, or sometimes we go down for this side, but the angle is always started over here, okay? Now, let's name these things. If we go straight through this angle and go out this way, right through the angle and go out, that's opposite of the angle, right? And we call that side the opposite. Now, anything that's next to you is known as adjacent. It's adjacent to you, it's next to you. So next to this angle is the adjacent. Now, there's only one thing left, right? And I want you to notice, look at where the 90-degree angle is, and out across opposite of that is the hypotenuse. And the hypotenuse is always the longest side. So you have two hints where the hypotenuse is. It's directly across from the 90. That's number one. And number two, it's the longest side. And if it's not the longest side, you must be working with inverse function sides. Okay, which is done occasionally, but we won't get into that at the moment. So let me get rid of most of this stuff, because we want to just start calling this, get all this out of here. Now, even though we call this the hypotenuse, the adjacent, and the side opposite, when we're doing certain things, we're going to call those things by the titles of what they really are. Like in AC theory, the class next semester, the side adjacent in a resistance triangle is always the true DC resistance, which you guys know really well. But this opposite side is always the X sub L. Not the X sub C, but the X sub L. The inductive reactance, the resistance due to current, AC current flowing through a coil, which doesn't have the real instantaneous resistance like DC resistance does. It has resistance that's the result of building up a magnetic field and collapsing it, building up a magnetic field and collapsing it. But it's like jumping up and down on a pogo stick. You know, you're using a lot of energy doing it, but it's not going anywhere. You're not going forward. You're not making any progress, right? You're just standing there burning energy, right? Same thing with X sub L. You're building a magnetic field and collapsing it, and it doesn't do anything. And the less we do of that, the better. But that's all a whole different opera. The hypotenuse is the result of these two things. When we're talking about resistance triangles, where we have resistance and X sub L or X sub C, or X sub L and X sub C, the H is no longer just called the hypotenuse, it's the impedance, the total resistance to AC flow. Go ahead and write that down. Impedance is always the total resistance to AC flow and has the symbol Z. Z is equal to side Z. So A might be R, O might be X sub L, and H might be Z. But it doesn't matter at all because it's still the adjacent, opposite, and hypotenuse. And we're going to treat it like that. And as long as you remember that this is the adjacent, that's the opposite, this is the hypotenuse, this will always stay simple because this is a simple relationship. It's a fractional relationship, a fraction. O over H. Let's look at those sides. The O compared to the H. Now if I make this triangle a lot bigger, as long as I'm maintaining the same angle down here as this one up here, the proportion between this side and this side is going to stay the same. It's like when I'm looking at, well, we'll talk about that in a second. We'll come to that in a second. So let's look at, now that is, uh-oh. My drawings have gone away. Okay. No problem, I guess. Let me hit pause for a second. Okay, so back to where we were. The sine is always the relationship between the side opposite and the hypotenuse. And it's just a fraction. If you've got, let's say, 10 here and 25 in the H, then it's 10 over 25. 10 divided by 25 is 0.4. 0.400. That would be the sine of that angle if that's the opposite in the hypotenuse. It's not very tough, right? A simple idea. And that helps us because once we know the angle, then we know three pieces of information. The relationship between the opposite and the hypotenuse, the adjacent and the hypotenuse, or the opposite over the adjacent. Now the sine is the opposite over the hypotenuse. The cosine is the adjacent over the hypotenuse, and the tangent is the opposite over the adjacent. Let's look at the opposite over the adjacent, the tangent. Now, tangent can be over 1. That can be a fraction that's over 1 sometimes. It's the only one that's ever over 1. Now, what if the side opposite is 10 feet? Pardon me, 10 feet. And, no, we want to go, I'm sorry. We want to go from the leaning the ladder rule. For every 4 feet up, you've got to go out 1 foot. If you're leaning the ladder against the wall, OSHA says you should lean this ladder. For every 4 feet up, you need to go out 1 foot at the bottom, right? So that you don't go flipping over or sliding down or whatever. So that's a good angle. Well, you might ask, well, what is that angle? We can figure that out in a minute. We'll come back to that. But I want you to see that if we go on up, way on up, to say 40 feet, and we know that's going to be way up there somewhere, we know that this is going to be 10 feet because 4 to 1 is the same fractional ratio as 40 to 10, right? We've just multiplied the numerator and the denominator both by 10. We've scaled it up, or we could scale it down. And that's the neat thing about the fractions. If you know the angle, then you can scale it up or scale it down. So what that means is that once you have the angle and any one side, that one side will set the scale, the size of the triangle, right? So any two sides you can find the angle, or if you have the angle on a side, you can find any one side, you can find everything else. So let's look at a couple of uses of this. Now, the cosine, by the way, is a very important thing in electrical work. The cosine of a power factor, is the power factor when you're looking at the phase angle of a circuit. And this angle right here, when you're looking at circuit totals like the resistance and the X sub L, that angle is called the phase angle. And that affects the power, how much power the circuit's working. Okay? How much apparent power is being turned into true power, and because of that, the cosine, or the phase angle, is called the power factor. Okay? So it comes up all the time in electrical work. But let's look at a simpler use. Let's assume that we just want to bend a piece of conduit. So let's just assume, now, an offset is where we kick up and we go over some object and then we go back to level. And let's assume that we have a 12-inch object we want to go get over. So now let's assume that we want to kick over because of some obstructions in the way they're cutting across our path. We can only get in a certain place. And we stuck a stick in there and we realized, well, we need to be about 30 degrees. Except 30 is too much or too little or something, but we're going to say we need to go about 35 degrees to be able to get this conduit into the area we need to get into. So if we know that we've got to have about a 35 degree angle, that means we're going to bend this conduit up 35 degrees, and then back here, we're going to take it back down 35 to make it level. And if you flip it over properly, it won't have what's called a dog leg, and it'll look just perfect. It'll go straight down the run, and it'll go up, it'll go back to level, and it'll just look perfect. It'll be a great thing. But what we need to know when we're bending conduit is how far between the marks do we need to bend it? What's the distance between these two 35-degree bends? Now, there's a couple ways we can do this. We can look at this and say, well, look at that. We've got a triangle here. We know the side opposite is 12 inches. And we know the angle is 35 degrees. So whenever we're looking at our functions, we want to find something we have and something we're looking for. And in this case, which function has something we have? First of all, the side opposite is what we have. There's only two functions that have the opposite in it, right? And we're looking for the hypotenuse. Well, there's only one function that has the opposite and the hypotenuse in it, and that's the sine. So, pardon me, let's pull out our handy-dandy TI-30X2S. I need to cough, hang on. So what we're going to do is we're going to pull out our handy-dandy TI-30X2S. We're going to hit clear a couple times. We're going to hit sine 35 and enter. Don't tell me I lost all my drawings again. Where did I killed it by touching the board again? All right, let's try this one more time and see if I can touch the board and erase all my markings again. So anyway, we're going to go up 35 degrees, and we're going to use the sine to find it. What is the sine of 35 degrees? And that's equal to, oh, hell. Except that we know one of those. We know the side opposite, don't we? So we're going to plug in 12 over h. So now we have two solid numbers. 0.5735 is equal to 12 over h. Everybody agree with that so far? By definition of everything we talked about. Now, you got to remember that anytime we have a is equal to b over c, we can multiply both sides by c. That'll drop out. And we'll have this. And then we'll divide both sides by a. And that'll drop out. And we'll get c is equal to b over a. In other words, we can always just take these two and just exchange them. Okay? So, if we just take this and we exchange them, we wind up with h is equal to 12 divided by 0.5735. Now, we've got 0.5735 in our calculator, so all we're going to do is punch in 12, divide by second function, answer, enter. Point what? 92. All right, now here's a problem with that answer. That's in decimal parts of an inch, right? How much is 0.92 inches? Well, now we need to go, electricians use tape measures, and they have sixteenths and eighths. They don't have 0.9, 0.95, 0.92. We don't have that. So we've got to find the nearest 16th of an inch. Okay? So the last eighth before a hole is 7/8, right? So 7/8 is 7 times 0.125, because an eighth is 0.125, right? 7 times 1.25, 7 times $1.25 is what? 875. Okay, 0.875. Now, is that close? 0.875? Not close enough. So you know it's going to be the next 16th, because 0.9 is only 90%. So you know that another 16th. What is 1/16th? 0.0625. 0.0625. So if we add 0.875 and 0.0625, we'll probably find the closest 16th. But as someone said just the other day, we could take this decimal point, 0.92, and multiply it times 16. And that'll give us the nearest 16th. 16th. Sorry. And that comes out to a little less than 15/16, right? So it's on the shy side of 15/16. So 15/16 is definitely the closest. So if you go to 15/16, 20 and 15/16 on the tape measure, and draw the line just slightly behind 15/16, you're going to be right on the money. It'll be so close that even with 6-inch rigid mounted 2 stories high on a building, right next to the freeway in Van Nuys, people going by the freeway will not be able to see any discrepancy in that. Did you know that if you're off 1/8 of an inch in a kick, if it's 2 stories high on the freeway or people driving by on the freeway, when they see it, they'll be able to see that it's off. Your eye is that discriminant. Your eye can see level miles away. And when something's even 1/8 of an inch not level, you can see it like it's standing out, like somebody beat on your thumb with a hammer. Your thumb is bright red and throbbing, and that 1/8 of an inch off, even though it's 6-inch rigid, 80 feet in the air, next to the freeway in Van Nuys, you'll be able to tell if it's more than a 16th off. And all that conduit on the outside of Budweiser up high, that 6-inch rigid, that is, if you overbend it even 1/2 degree, you can't get it to go back. You can't get it to go a little more. You can't get it back in the machine, take a little more. You got to make it perfect every time. Or cut it up and start over. I ran all that conduit. And even from the freeway, you can see, hey, that's all level. Hey, look at that kick. It goes around and it's concentric around there. It goes up there. Oh, that looks nice. from miles away. And literally, you can see an eighth of an inch off if it is. We found that out the hard way when somebody else, well, we won't get into that. So anyway, so this is how we would do an offset where we can't use what's called a standard multiplier. A standard multiplier is like if you're going to kick up 30 degrees, whatever the obstruction is, you go twice that. Very handy multiplier, right? But we won't get into that. So then this is used, the sine, cosine, tangent is used in circuits. Let's get a new slide. This time it's intentional. Okay, now let's talk about power triangles and resistance triangles. Now this is what I call simultaneous triangles. Let's talk about a real circuit. Let's pick a voltage. What voltage are we going to pick? So the voltage is a little low in this area. And this motor draws how much? Or this circuit draws how much? 5 amps. Good. Okay. Now you remember when we're talking about AC circuits, we don't have R down here anymore. We have Z, the impedance, the total resistance AC flow. We're talking about 110 volt AC circuit. Okay. Now, one thing you can read with your meter is the current coming in, the voltage coming in, and the resistance of the circuit. And let's say, well, let's find out what our total impedance is first. What's 110 divided by 5?
22.
You got a calculator? 22 ohms of resistance. Now let's say that we take a meter and we measure the resistance of this circuit and that it's 14 ohms. And as I said, resistance always goes to the bottom of the triangle. Okay? Now, let's multiply this up. If we have 5 amps at 110, how much power is that?
70.
Your calculator's failing. 5 times 110 is 70? Thank you. And is that watts? No. Volt amps, apparent power. What's coming into you from Edison, or whatever utility it may be, whatever voltage and current you're getting, that's the volt amps. Volts times amps gives you volt amps. Not a hard concept, and that's called apparent power. That's what's coming to you. And I don't care what Edison says on their bill, that is not watts. Watts is the real work that's getting done, which is a proportion, a fraction of the apparent power you're taking in, and it's called true power. And the apparent power, now this is going to be the power triangle over here. Power, apparent. Power, true. And over here we're going to have X sub L, and up here we're going to have Z. Don't we already have Z? 22 ohms. So we just found out something about this circuit, right? So now I have a question. We have two sides of a triangle. What function do I have? Is it sine, cosine, or tangent? I have the hypotenuse and I have the side adjacent. Oh hell, another hour of agony. We have the cosine. Okay, the cosine of any angle is A over H. Oh hell, another hour of agony. Okay, now that means that we could find this angle by saying to our calculator, tell me what angle has this cosine. And we're going to do that by, let's hit clear one time real quick. Now, hit second function, cosine 14 divided by 22, enter, and it's now going to tell us the angle. .50? Is that right? That's the number of degrees. Now, I want to simplify this for a second. Hit clear. Everybody hit clear. and just divide 14 by 22. Divide 14 by 22. What fraction do you get? 0.63 what? So the cosine of this angle is 0.6363 continuously. Oh no. Oh. Nope. All right. On the set. Right on the set. All right. So back to our triangle for the third time. So we found our angle. What was it? No, 550, 47 degrees. And the cosine of this angle is 0.6363 and on and on. Okay. Now, we're not going to worry about the XL at the moment because that's something that's hard to measure. You can't measure the X sub L. Or it's very difficult to measure it. Let me rephrase that. You have to infer it. You have to do the math, as it were, to find out what it is. Now, the cosine of this angle, this is called the phase angle. Now, the power triangle of that same circuit will have the same exact angle, except instead of it's going to be set to a different scale, it's going to have 550 VAs up here. Okay, so we've got a different triangle. Now, the cosine of the phase angle is called the power factor because it tells what percentage of the incoming power is actually going to be converted to true power, the work that's getting done. And we can see that if the cosine is 0.6363, that 63.63% of this 550 VAs is going to be turned into true power. Let's multiply 550 times 0.6363, which is in your calculator at the moment, right? So we just hit times 550. And we get no. No. Well, it's over 250, so what was it? 350. Let's call it that. And what is this? Now, this is watts. This is how much work this circuit is actually doing. And that becomes an important factor. Now, X sub L is a result of impedance because of the winding of the coil and the field being built up and collapsing, and there are things we can do about that. But that's for another day. But we can find that. How could we find this if we wanted to find the X sub L? We want to find a function that, now we have the angle, so we have all the functions, right? So now we can use any of them. And we want to find the side opposite. Oh hell, another hour of agony. Which one of those so we could use sine, cosine, or tangent because, or we'd use sine or tangent because both of them have the side opposite, which is what we're looking for. And one has the adjacent, which we have, and one has the hypotenuse, which we have. Let's use the sine. So we have the cosine. Let's do this again. Let's get the exact answer. Let's go second function cosine 0.6363636363 and hit enter. And now we'll get a really long number where we have 50.47 and a whole lot of numbers behind it. Now we have the exact angle, right? So now let's hit sine, second function answer. That will give us the sine of this angle, which is okay, the sine of the angle is 0.77138. Okay. Now, what is the sine? It's O over H, right? I need a little more room. I'm afraid to touch anything, though. Sine of theta is equal to 77138, 0.77138, and that's equal to O hell. Now, we know one of those, right? We're looking for O, and we know the hypotenuse. We're talking about this triangle over here. No, we're talking about this one over here. So we're going to put in 22. Now, to get rid of the numbers on one side, we can just multiply both sides by 22. So 22 times 0.77138, which is in our calculator right now, right? We just hit times 22. So in other words, about 17 ohms of X sub L. And in the future, someday, one of the things you're going to want to be able to do is find out how to get rid of that X sub L. And how much of it do you want to get rid of? Do you want to get rid of that? You want to get rid of not all of it, but at least 95% of it. So if you want to get rid of 95% of that, because overshooting is worse than being a little short. So we want to just take it down some, mostly. We want to get close to 0 degree angle, perfectly efficient, but better to be a little short than blasting past. So generally speaking, we'll take 95% of that and try and fix that circuit. But that's, as I said, for another day. Okay, so that's one of the purposes. This is a simultaneous triangle problem. So let's do one more. And we're going to talk about, again, we're going to talk about a real circuit. And let's assume that we are given, 240 volts at 4 amps. Those are both things we could read with a meter, and we could then find out by calculation that our impedance is probably around 60 ohms. And let's say that we took a reading on this circuit and it had about 40 ohms of pure resistance. We now know the angle, right? We now know the apparent power. How much true power is this circuit making? Well, first we need to find the angle, right? What is this angle? Well, it has a cosine of 40 divided by 60, right? That sounds familiar. Where have I heard that number before? 0.6666, 2/3, right? Okay, so it has a cosine of 2/3. And we can multiply up 4 times 240. And where would we put that? Yeah, I'm sorry, it is 960. 4 times, not 2. So we're going to plug in 960 VA is over here in our power triangle. And we've kind of resolved this. We know that this has what degrees? Second function cosine 0.6666 enter will tell us the angle, right? What angle is it? Say again? 48 degrees? 48 even? 19. Okay, 48.19 degrees. Now, if we know that, we can come over here and we can say, well, the cosine of the angle is our power factor. So we could take this 960 and multiply that times 0.666, which is, I think, is still in our calculator, right? Or we could hit clear and just enter 0.66666 times 960. That'll tell us this side over here, won't it? Why is that? Because the cosine is equal to 0.666, and that's equal to another hour. Oh, hell, another hour. And we know the hypotenuse. So it's A over 960. So if we just multiply 960 by both sides, this will drop out. We'll get 960 times 0.666 is equal to A. So if you just find a function that has what you have and what you're looking for, that's the function you're looking for, right? And then start plugging in things you know and finding things out. And then find another place where you can find something you need and something you have. Pretty simple, right? Okay.